Okay, so now let's talk about drawings. Aircraft drawings are essential to your existence as an aircraft maintenance technician. Now, different kind of echelons and modalities of aviation maintenance will use drawings a little bit differently, or maybe not differently, but to a certain degree of fidelity. How about that? General aviation, the drawings definitely exist that are out there, but from my experience, at least, like a lot of GA mechanics basically kind of go off of experience more than they do actual, like engineering or maintenance instructions and things like that. However, once you step into the corporate world, this stuff gets a lot more expensive, and people get a lot more serious about sticking to by the book maintenance. Definitely in the military, if that's the route that you're wanting to go, you'll get by the book maintenance beat into your head. You get into heavy commercial stuff, everything is going to be per the aircraft maintenance manual or something. You get into aircraft construction, manufacturing. It's a lot of fun. Everything you're going to hear the drawing over and over and over again, to the point you're going to be nauseated with how much fidelity it goes to the drawing, because you're trying to make an aircraft that's going to carry people, and it has to be built to spec. So knowing these drawings is extremely important for you to be able to do your job and do your job well. And I'll tell you, if you can read an engineering drawing and know what needs to go where and how to manipulate that data to make the aircraft work, you're going to be in high demand, because there's a lot of people out there that struggle with it for whatever reason. One of the biggest struggles you'll see is people just rush through it. It takes time to kind of slow down, look, get the right information, think through the problem, and then move forward. And a lot of people want a quick and easy answer, and they just gotta look at it and go, oh, okay, let's just take off. And there's just too much detail on there, and it's written in such a way that you really need to pay attention to those details, or you'll miss something. So let's go through some definitions, and we'll flash on the screen different pictures as we go. So first definition we need to know is the title block. So one of the first things that you'll need to know about an engineering drawing is the title block. What does this drawing really cover? So the 8083 says the title block consists of a drawing number and certain other data concerning the drawing and the object it represents. So the drawing number is really important. That's how you know that you're on the right page. So that's in the title block. And we should be able to get to revs. Revs are another real important, like different revisions. And you'll hear people say, like, well, they just revved this drawing, or they just revved that manual. That's what they're talking about. They've updated it. There was a point in time where printing off manuals was kind of commonplace, and then what ended up happening is that, like, they would rev a manual, they'd rev a drawing, and it would supersede the drawing that was printed out, and so it became a kind of a no-no to print anything out and keep it for more than a day, because you never know whenever the manufacturer will push out a rev, and you might be building, fixing, troubleshooting something to a non-standard state. All right. Reference numbers and dash numbers. So reference numbers that appear in the title block refer you to the numbers of other prints. So all that's basically saying is that, like, it'll say, hey, and you'll see this a lot, for more information on this, see drawing 1234-12B, and it'll point you to the right direction. A lot of times, especially whenever I worked at Boeing, we'd end up playing the drawing game, where we would go to the drawing that the job had referenced, and then that drawing would reference you out to another drawing, which would then reference you out to another drawing, and you would play this daisy chain until you got the information that you would want. You might have to go through 5 or 6 drawings to get to answer of one question. All right, dash numbers on the reference numbers are also used to identify right-hand and left-hand parts. It's just something to know that it'll say, like, dash, 1B or 2B or whatever, 1LH, like one left hand. That's what that's referring to. stuff too. Okay, a bill of material. Bill of material, especially if you're doing any kind of modification work, STCs, even like whenever I was doing the go-go internet upgrades on the Southwest Plains. One of the first things that you would do if you were, especially if you're the first person to get on that job, is they would give you a kit, and on that kit there you'd have like all your drawings and all your hey, do this, do that instructions, but it would come with bill of material. And the first thing that you do is take that bill of material and lay out everything and make sure that everything that's on that bill of material is in that kit. Because what will end up happening is that somebody, say like Carlisle, will end up having a fight with their girlfriend the morning of, and then the whole time they're thinking about the fight with their girlfriend and they're not counting parts and pieces. And so what will end up happening is that you'll get halfway through it, you'll be like, oh man, I was supposed to have 5 screws, but I only have 4. Like, where's the 5th screw? And then it becomes this panic moment of like, did we fought out the airplane? Is the screw somewhere here? And you take everything apart. You're like, where is the screw? And then next thing you know, everybody's like, look in your toolboxes, and everybody's pulling their toolboxes out, like, where's the screw? And there's all this drama because the screw was never there. And then it becomes like this like weird, almost ethical deal of like, well, do we say the screw was never there? And it's like, or am I just trying to take an easy way out rather than finding the screw, which doesn't exist anyways because it never had it. And so like this is like extremely important that you make sure you know the bill of material and you lay out everything. I mean, this is like just a good habit to get into. Even you buy IKEA furniture, take your instructions and say, oh well, like I see that I'm supposed to have 5 screws, but I only have 4. What's up, IKEA? And then you, at least you know that, well, you're always going to be short a screw. So that way you can annotate that and get it fixed early on and provide, make sure you maintain that level of safety and your own sanity. The bill of material is extremely important. So let's talk about notes. Notes are added to drawings for various reasons. The devil is in, not the details, the devil's in the notes. I've seen a lot of different situations where there's a lot of drama that causes confusion because there was some note somewhere that somebody either didn't read, or there was some kind of little nuance, or it said that everything that you're doing, don't do any of those things if these conditions exist, and that was in a note. So one of the things that's a good practice is that whenever you get a drawing, take that drawing and immediately just go like, okay, I have the right drawing, and then go to the notes and then read what's all the little details that they want you to know before you get like way into it, because it might be a situation where like you're tearing everything apart, doing all kinds of crazy stuff, but if it's this dash number of plane, well, you don't have to do all this stuff or anything like that. So definitely pay a lot of attention to the notes, even if they're long, they're worth a read. Unless it'll help you understand what's going on. Okay, zone numbers on a drawing are like numbers and letters printed on the borders of a map. Essentially, whenever you get a drawing, you're going to play Battleship. And so kind of like almost like going back to our conversation about the reference stuff, you'll see a lot of times where it's like, hey, move this and put it on, 1B. And so you're like, where's 1B? And so you'll go to this big, zone 1B, and it takes a big drawing. And sometimes these things, especially if you're in a factory, these things are big, and like there's a lot of information on it. And so like it's helping neck down the drawing to this like, hey, look, pay attention to this one little area right here, rather than having to, look all over the place. So those are zone numbers. Okay, station numbers and location identification on aircraft. Numbering system used on large assemblies for aircraft to locate stations such as fuselage frames. So these are going to be water lines, butt lines, station lines. So essentially, if you were to take an aircraft, and we'll put a picture up of old Cirrus Ascend 8083, but essentially, you're playing 3-dimensional Battleship on the airplane. And so if you're saying, hey, look, I'm looking for this part, all right, it'll give you a 3-point location. It'll say like, hey, look, it's at station 41, water line 21, butt line 22, or whatever the thing is. And that allows you to go like, okay, station line, okay, that gives me forward and aft, water line is like up and down, and butt line is, left to right on the plane itself. And so knowing like that may seem confusing, never having done it before, but once you kind of get into the rhythm of it, it's not that big of a deal. And it'll become like a conversation piece. They're like, oh, well, it's at 42 or whatever, like, where's the aft bulkhead located? It's always, these kind of credentials for aircraft mechanics. Like, if this guy knows where the 48 section is, then he's a real mechanic. so you'll start to see those things kind of creep in. All right, so allowances and tolerances are real simple. It's plus or minus. So like it could be 1 inch plus or minus an inch. So like it means it's actually got a kind of like a 3-inch range. So if it's 1 inch, we put it at 1 inch, but it could be plus an inch. So it could be 2 inches, or it could be minus an inch. It could be no inches. So it could be right there, 0. So plus or minus is just, think of a number line. It could be like a little bit over, a little bit under. And the reason why they do that is because like precision is a hard game. Trying to do everything exactly right every single time can be somewhat difficult, and so that gives you a little bit of grace to the manufacturer, the maintainer, that, hey, look, install this rivet, plus, like to, 21 inches, 0.02, plus or minus 1 inch, or whatever the number is. And that kind of gives you an idea of like, okay, like I could be right here. If I'm a little bit off when I drill the hole or whatever, it's still okay if it's inside those tolerances. But you definitely want to shoot for center line, or shoot for center on everything, torques, measurements, and whatever. Finish marks. Finish marks are used to indicate the surface that must be machine finished. So all a finish mark basically says is that, like, it was part of the drawing. Whenever you're done, if we're gonna bead blast this or powder coat this or whatever the thing is, you're gonna make it nice mirrored polish. It'll be annotated on there, and that's how you know. Scale is really simple. If it's 1 to 1, so if you had a 5'10", 200-pound version of a paper version of me drawn out that was like 5 foot 10 inches tall, then you would that'd be a 1 to 1 drawing of Brandon Sanders. But most of the time it's like gonna be like at least 1 to like 20 or something. It's gonna be neck down real significantly. It's because like you're dealing with like jets that are huge, and so like they have to be, in order to make it fit on a piece of 8 by 10 paper, it's got to be reduced pretty significantly. And so scaling is the way you do that. Okay, so a detail view shows only the part of an object, but in greater detail to a larger scale than a principal view. So all that's basically saying is like here's like a drawing kind of gives you like an idea, like, hey, look, this is what a 737 looks like. So detailed view is like, this is what a 737 looks like, and here's where like the antennas go, and here's the windows and all this other kind of stuff. But they're not going to be like so far in the weeds that like here's the individual rivets. That's all it is. Pictorial drawings are just like a photograph. So like a lot of modern manuals coming out, you'll see a lot of that, where it's like, hey, look here, it's basically like an AutoCAD picture where it's just like, bam, like here's the LRU or whatever we're working on, so that way you know what it looks like. So that way, whenever you're up in the airplane, you're like, what is this thing exactly? You're looking at all the data plates trying to figure out which one it is. Okay, so perspective view shows an object as it appears to an observer. So that way, imagine if you're like looking up into like an engine, it's like, so the perspective view of a guy on the ground looking up, it should look like this. And so that kind of helps you identify what the part is. Not too different than the pictorial drawing. Okay, an isometric drawing. Isometric views uses a combination of the views of an orthographic projection and tilts the object forward so that all portions of all 3 views can be seen in one view, which is a very wordy way to say like it's going to show you the same thing from different angles, and we'll put one up so that way you can see what that looks like. Oblique drawings. 2 of the 3 drawing axes are always at right angles to each other. Very similar to isometrics, just a different kind of a take on it. Exploded view drawings. This is the way a lot of GA maintenance seems to go. An exploded view drawing is pictorial drawings of 2 or more parts that fit together as an assembly. So essentially, an exploded view is something you've seen these before, whether you realize it or not, because people even use them as like showcase pieces in restaurants or buildings and things. That if you imagine like your car, and if you were to pull all the parts off of your car, and you would say like okay, well, here are like some lug nuts, and here's a wheel, and then here's a rotor, and there's a brake caliper like attached to it, and then behind it is an axle, and so on and so forth. It would show you like every layer of part and every layer of assembly on that. All we've talked to up to this point is kind of like engineering drawings about construction. We're going to start to get into the more of a maintenance and troubleshooting side of it. Installation diagrams identifies each of the components in the system and shows their location in the aircraft. So that's a pretty cool drawing to have if you can have access to it, because it's going to show you what right's supposed to look like. And so if you have an installation drawing, it'll say like, here's the installation, and this is how everything should be arranged and set. And so that way you can look at it, and at least if you're putting everything back together, like what standard you're working to. If you're inspecting something, you can say like, okay, this is what it's per the book. This is what it's supposed to look like, and then it doesn't look like that, so something's gone weird, and you start to kind of dig into that. Schematic diagrams. They locate components with respect to each other within the system. Schematics show us the principle of operation of an aircraft system and are often used for troubleshooting and training purposes. I will tell you, my life changed whenever I discovered Boeing's systems manual, or systems diagram schematics. The reason being is that the aircraft is very complicated. It has its own ecosystem to where whenever this component kicks on, it does this to these other components. And so a lot of times, especially doing any sort of avionics or any sort of electrical troubleshooting, various systems will talk to various other systems. And what you're trying to figure out is that why is this one system malfunctioning or doing something weird that we don't want it to do? And you're starting to try to figure out where's it, what's prompting this, or what's getting it going? And you would take a step back and you start to realize it's because whenever Pack 1's on, these things happen, and they may happen for a really good reason or whatever. But if it's not explicitly stated in any task, and it's not evident just by looking at it, you would never know. And so, but with the systems diagram, it lays it all out nice and flat to where you can say oh, well, if thing A happens, then B has to happen. And so you can start to trick the airplane by kicking thing A on to make this thing happen, or by turning it off and trying to take that data input out of the equation. And you can start to isolate and start to neck down where you're trying to or what you're trying to work on. And so know that your systems diagrams really well. It won't give you the super fine detail to actually fix a problem, but what it will give you is an awareness of what's going on the plane whenever some event has occurred. Okay, block diagrams. Block diagrams are used to show a simplified relationship of a more complex system of components, and we'll put one that's pretty straightforward. Wiring diagrams, my personal favorite as an avionics guy. So wiring diagrams show the electrical wiring and circuitry coded for identification of all the electrical appliances and devices used on an aircraft. So wiring diagrams are kind of their own beast. AMMs, your maintenance manual, they're very they're trying to write it for the lowest level of mechanic, to where it's take this part off, put this part on, torque this part to that. Engineering diagrams are set up for people doing construction, and so there's a lot of detail that you probably won't ever necessarily need, but it's there if you do need it. Wiring diagrams are interesting. You'll have different connectors, different breakouts. You'll have components that are located in the middle of that. You'll have all manner of things, and so becoming components. If you start looking at the different components list, and we'll get into that. We'll get into all this a lot more when we start to do basic electricity. For now, just know that wiring diagrams are kind of their own almost subset, because there's so much going on a wiring diagram. Okay. Flowcharts. Flowcharts are used to illustrate the sequence or flow of events. It's pretty simple. It's just going to say okay, well, whenever the pilot assigns for the aircraft, it's now the pilot's aircraft. Next, and then you'll see an arrow that says like, okay, the pilot then gets on board the aircraft. And they say, okay, well, cool. Now the pilot's on board the aircraft, he's going to turn the aircraft on. And then it's going to be this sequence of events, or, you know, like if this, then that. So like if the pilot gets on the board of the aircraft and there's no fuel, well, the pilot gets off the aircraft, and that'll be another event on there. So it's pretty easy to follow those. Troubleshooting flowcharts are a thing. I haven't seen them be super duper reliable, just because the airplanes are really complex, and troubleshooting flowcharts try to make them simple, and they're just not simple. So like what will end up happening is you'll say like, okay, well, if this is the fault, so like the fault isolation manual for most your Boeing aircraft, your FIM, the FIM will say like, if this is the fault, we'll check this, this, and this. And all it is that some engineer sat back and said like, okay, well, if this is doing that, then it has to be this, then it has to be that. And they seem to plan this in like somewhat of a vacuum, and so like they're not wrong. They're like, yeah, like these are the things that may be happening. But whenever you start nesting multiple systems and they're all talking to each other, the plane breeds its own ecosystem, and so all kinds of weird stuff can happen. So a FIM is a great place to start working through it, but there's always going to be these like weird nuances and things that no one anticipated that come out of it. The technical term for that is emergence. Like you'll have new faults emerge from the complex system, because it's not just the aircraft, it's also the environment, the people that have worked on it, the individual configuration. All those things start to factor into this. So FIMs are good places to start, but generally speaking aren't the thing that's going to save your bacon. Okay, logic flowchart. We're going to get this more when we start talking about digital logic, but it's developed specifically for the analysis of digitally controlled components and systems. So those are your and, or, nor gates. It'll be a lot of fun. They can also be really complicated whenever you say like, you'll have like a symbol, and like I said, we'll get to this a little bit later in more detail, that'll say like, hey, look, if we have this control or this input coming in and this input coming in, then the output is this. But if you don't have one of those two components, the output is something different. All right, so here's an example of a drawing. We're going to go over it. And so here's our title block right there. Notice there's our drawing number, our rev number. Don't worry about the cage code or size, but here's our scale. So we know it's a 1-to-1, so this is the size that this part actually looks at. Here's our different zones. So if we wanted to say like 2D, here's 2, and here's D. So you notice there's just nothing there. So let's say, here's a kind of a check on learning. If I wanted to say, let's ask like, what's in zone 5B? So we'll say like, here's 5, come up, here's B. It's like, oh, well, the dimensions for how tall the part is supposed to be is in 5B. And like it says, for revision history, see sheet 1. So this is going to be sheet 3 of 3. This is something that we didn't cover in our definitions part of it, but here's sheet 3 of 3. Different drawings, this is especially true with wiring diagrams, will have multiple sheets, and so you want to pay attention to that like if there's something you're not finding or something you're confused about, a lot of times it's on another sheet. And so like, if you're like, I just can't find it, come down and be like, oh, well, it's sheet 1 of 4, and then go find the one that you absolutely need. All right, here's another sheet another example of a drawing that has a little bit more in it. So we'll just go through all these. Here's our title block, just like we did on the last one. Notice that it has all the information that you possibly could ever want to know about this drawing. Here's our bill of materials that we talked about that was like really essential. So notice that like it'll have like, nut anchor, 1 lug, 1032, and they'll say like, hey, look, this is the quantity that you need is right here. And then here's the item number 5. And so here's item number 5. You need 4 of those guys. And look here, there's 1, 2, 3, 4. So whenever we inventory our kit, we'll know that we have all 4 of them. We're good. We can go on to the next thing. Here's our drawing number on this one. Drawing number has all the information we need. Notice the sheet numbers, 1 of 3. Here's our revision block. This will say, like, notice there's no rev here, but then here's rev A, revise per ECO 222276. Remember what I was telling you about trying to play the drawing game of where did the drawing go. This is where it starts. So he'll say, like, per this. I'm just like, okay, cool. Then you'll get to this, and it'll say, like, this was revved per that. You're like, okay, like, you keep on, you'll just follow it all down if you're trying to get to an answer. Another interesting thing to kind of just know is necessarily that's going to have a huge impact on you. This is the guy that actually checked it. In bigger companies, you'll end up seeing a situation where the guy who designed and built this part is not this guy that's checking it, and so sometimes they don't know anything. But sometimes you'll get to where, like, the guy that actually designed and built the part is the guy that signed off on the drawing, and you can call him up and be, hey, like, what about this, or what about that, or why did you do this, or have you ever thought about that? And that's a good thing that you can kind of talk back to the engineers whenever it happens. And also, this is the date. So, like, this is actually a really fun one to look at, because the last time the drawing might have been touched might be like in the 1970s or something like that. If it's like an older, like a 737NG that maybe hasn't changed just a whole lot on some of the structural stuff, at least. All right, so we do D, E. Here's our notes block. All right, so notes says finish chem film per this mil spec. Type 1, Class 1A. And so you'd have to look up that mil spec to know exactly what it's talking about, but it kind of gets you in the right direction. Part will be marked IAW in accordance with STEC SOP 3-03- or 3-0-03. So, like, to get to know, like, those little terminologies in accordance with is a very, very popular one. So mark part number and revision letter in contrasting color and characters. So mark the part number and revision letter in contrasting color characters. So, like, to be manufactured per the drawing, you need to mark the part number and the revision letter. So this is going to be Rev B. No, I take that back. Rev A. Sorry. In contrasting colors. So if this is black, it needs to be in white or whatever the thing is. All bin radii shall be 0.125. So that's just saying, like, hey, look, kind of instead of writing all that stuff out every time that there's a bend, every time that we roll metal, there's this information that needs to go into it. So instead of having like an arrow or a line like that tells you this stuff, it just says, like, hey, it's in general all 0.125. And usually if you're doing a lot of this type of work, like, those numbers will become like, oh yeah, and like you're looking for the notes to see if there's an exception to it rather than a policy. And all corner radii should be 125. So they're trying to not clutter this so that way you get lost on it. Remember when we talk about human factors, like in the shell model, one of the things they want to look at is just like, hey, look, were the instructions really, like, confusing? And so imagine if you put 0.125 on every single curve that's out there in every single bend, it would get really messy really fast, and it would be very, very confusing. So that's it. Zone numbers, we talked about that on the last one. Allowance and tolerances, this is something to pay attention to. So it'll say, like, hey, look, the standard for this drawing is you can round to the whatever, decimal place or whatever the situation may be. So know that and pay attention to your allowances and tolerances. We talked about scale too, this is a 1-to-1. So yeah, so engineering drawing right there. Here's an actual one that kind of shows you what it is. I'll give you a moment to look at it. Notice that we have, just start with our drawing number. Then, the scale is 1 in 32. It's got 3 sheets. What else do we want to know about this? It'll refer out somewhere on here. So 2, there's our reference blocks. It's another thing that the 8083 didn't cover, but essentially, like, these numbers will correspond to things inside the reference block or in the note section. So notice the phantom line, and it tells the intersections of aircraft removed for clarity. So it's like there's probably a bulkhead right here or something, but they took that out so that way you can see what's going on, because it looks like this probably goes in the floor. Notice our dimensions right there. This is a detailed view. So here's detail B, detail C. Okay, so we talked about this a little bit. Let's do it like this. About 3-point locations on an aircraft. So remember, so station lines will go front to back like that. So they don't really do a super good. Oh, there it is. Okay, yeah. So station lines will go front to back. So here's station 0, all the way back to the tail, station 350. All right. So if I said like, hey, look, like what's at some, such and such a station, you would come down here and say, oh, at 150 is the door. All right. So that's water lines. Water lines are up and down. So the door sits at, water line, say 100 is like the bottom of the door scene. If we wanted to go center mass on that, it'd be like, say 125 looks about right. Maybe 120, maybe a little bit lower than that. And then buttock lines. So buttock lines are, left to right. So like here's our center line, buttock line 0. And then if I said like, hey, let's go to, the 50 right buttock or say like our right buttock line 63-1 that's the wheel. There you go, right there. So that's right buttock line 1. So here's a little check on a learning for you. What is at water line 160, station 150, and left buttock line 63, 61? So if you said like the wheel pant or the wheel, the left main gear, that's it. So yeah, that's our 3-point locations. And know this pretty well, and you'll get to, the more you do it, the more you'll start to do it. So like I said, different stations mean different things, and people will start using and say like, oh, the baggage door's at what, probably 210, or station 210. So anyways. Another one that we don't want to get too far in the weeds with it today, just because we're talking about engineering drawings, and we're going to save a lot of this for whenever we start doing wiring diagrams and doing electrical troubleshooting. But just know that like inside of the world of wiring diagrams, there's a lot of symbology. Now, a lot of this may seem overwhelming. You may be even tempted to go through and memorize all this stuff. The best way to learn this stuff is just simply to start troubleshooting and just encounter them. You might want to print this off and keep this in your pocket while you're going, so that way, but as you run into something, you're like, oh yeah, I can remember X, Y, or Z. So like even the different types of circuit breakers. There's a push, reset, pull off versus the switch type of circuit breaker, and there's definitely both on there. You'll see a lot of diodes. I don't see diode on here, but this, I guess I don't. Different types of buttons, contacts, lamps, red light, green light, white light, all that good stuff, condensers. All of these things you'll become much more familiar with the more that you troubleshoot your different electrical circuits and use a lot of your wiring diagram knowledge. Learn to do it. Okay, so here is graphs. That's another type of drawing, another type of a way to transmit engineering data. This one, it shows the density of variation of aviation fuel based on the average specific gravity. And so you would say, hey, look, if the temperature is 0 and we're flying, Jet A or say like 100 low lead, I would say, okay, the temperature is 0. I would come up and say, okay, well, I've just intersected the 100 low lead aviation gasoline grade, and I would come over and say, okay, well, the specific gravity looks like it's about, not being super precise, just a little bit of below 6, and so I'll say, okay, cool, and that would help me make a decision. But you'll use a lot of different graphs over time, especially. I mean, I was doing an annual on my plane the other day, and I had to correct the spring or the tension of the cables for temperature, and the way I did that is I used a graph from Piper's maintenance manual. So this is something that you'll do on a regular basis, and it shouldn't be anything that's just totally new to you. There's the graphs used all over the place. This is a really good way to get into aviation. A good thing for you guys to know. All right, so what we have is a position light that's not coming on. And so what we're gonna do is we're gonna use some of our newfound drawing knowledge to help us troubleshoot it. So first thing that we did, I should have got this on camera, is we pulled off the housing, or the covering that keeps the light safe. So we removed the 2 screws from it, and you can see on the exploded part drawing how it comes out. Now pay attention to the main drawing that's up here, and it tells you, hey look, you're working on detail B. We come down to detail B, and here's the whole thing. So let's continue. All right, let's say that we remove the bulb and the bulb didn't solve it. That we looked at the filament on the bulb was good. We maybe moved it over to the other side and it also worked. So now we have to kind of elevate our troubleshooting. What drawing should we use? Well, we'll go to our wiring diagram. Now, when we look at the wire that is attached to the housing on our position light that we're trying to fix, we look on the wire and we see that the wire number is Lima 17 Golf 20. So we would come over here to our wiring diagram, and we'll put this up on the so you can see it. And we would find Lima 17 Golf 20, and it says, okay, left nav light. And so from there, we would be able to, check for power. We would also be able to shoot continuity through the splice. If you track back, there's a splice where it breaks out to right nav light, left nav light right there. And then there's also, it connects to another connector that's labeled P380, it looks like, on pin 16. And you could continue to, let's say we determined that the connector was actually what was bad. What we could use then, the contact installation guide, which is an exploded parts diagram of how it's supposed to be built up. Now this is a general one, it's not for that specific connector, but it is close enough to where we can use it for, our demonstrating purposes. You can see that there's the stack up of how everything is supposed to go. So that way, if we were to remove that contact, say the pin was bent or it had been corroded beyond repair or something like that, we would be able to manufacture that pin and then put it all back together per this diagram. And then on our sign off, we would cite this saying, remanufactured contact per 20-30-01. And so that's how you use the engineering diagrams and drawings to facilitate a repair.